there. Oracle's distributed cluster for computing framework was there. There is another toolkit called Globus toolkit. I don't know how many of you will know. So all these toolkits were not able to make the distributed computing parallel, but only Hadoop was able to make it. So we'll try to understand why and how it could break the barriers. Okay, so that's the essence. So I'm going to the next slide. So I'm sure you must have known about Moore's law, right? So you know that if you want to run a program in a computer, it requires input, output, CPU, right? And in the CPU, it depends on how many instructions it can execute at the same time, right? So it all depends on how many instructions can be executed based on how many transistors the CPU can have, right? How many logics the CPU can execute, how many arithmetic operations the CPU can execute, things like that. So a gentleman called Moore has predicted that every 2 years, the density of transistors within the CPU doubles, right? And it has been like that till 2011, every 18 months since 1965. So it has been like that since of late till we got i7, and you were aware that from Pentium onwards they started they started using dual cores rather than going for a single chip. So what they did is they hit the theoretical limit in terms of the frequency that the motherboard can take. So if we pump in more bigger frequency, then what is happening is the interference between different components in the motherboard becomes extreme, and then the stability of the system will go down. So from Pentium 5, not Pentium, I think later, Pentium dual core has come just for this purpose. What they did is instead of having one core, they just replicated cores in the same CPU system so that they'll get double the density. At the same time, they'll get double the computing capacity. Okay, let me close this here. So this is latest in the sense that digital computers, as we know, uses ones and zeros to do some computation. The machine understands only ones and zeros, and then initially when people started building computers, they built instructions using ones and zeros. Then they thought it is not easy for non-computer users to build ones and zeros. Then they said, okay, let us build something above it. Then they started with an assembly language, right? Assembly language is more like, okay, you have a mnemonics where you would be able to use add, subtract, do, multiply, move. These are the kinds of instructions that are available in assembly language. So then people thought, okay, non-computer users would be able to use computers or program computers. Then assembly language became little more than what people expected. So they said, no, assembly language is not enough. So let's build something else. Then they started building some higher level languages like Fortran and Pascal and things like that, COBOL. Then came C++, right? Then all these languages have come. Then there are fourth generation languages like 4GL interpreters like PHP, Python, Java. Those things have come so that the people will be able to program to computers very easily. But underlying architecture is that everybody has to convert from all these instructions have to be converted into ones and zeros end of the day. But today experiments have been carrying out for quantum for quantum computational operators where the light is being used for computation. So this is the kind of research you would see. So in future, you would see probably a mobile would be as powerful as an i7 processor today with this kind of technology. So the size of the CPU and size of the motherboard and size of the components are going to become much smaller with the new technology called quantum bits. It uses some of the technology using the semiconductor technology and also light. All right. Again, this is just comparison of Moore's law with an illustration. In 1970, the number of transistors in a CPU were about 2,300. So if you compare with an average music hall, I think it's about 2,300 people in a hall. But today, Core i7 has about the size of the population, the size of transistors is about 1.3 billion, equal to the size of the population of China. So that's how much density we have today. Okay. So naturally, the computation power has gone up. So then the CPUs have moved from 8-bit to 32-bit to 64-bit now. Now most of the processors are all 64-bit. So you can save bigger numbers. You can move the 64-bit of data into the registers much faster. So computation has become much faster too, right? So again, today you can what can we do with one single computer? At the most, you can run a browser, or you can run some calculations, or you can do solve some mathematical problems, right? But can you actually analyze gigabytes of data or terabytes of data? Let's start with an astronomical data. Let's say if you are observing stars and data is being downloaded at a fast rate, and you will see that gigabytes and gigabytes of data has come in. Now, with one computer, in order to process all that data is not enough. For example, today, if you see, you might have seen that the 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 hard disk speed to store the hard disk speed to store data started from 10 megabits per second, then 33 megabits per second, 100 megabits per second. So we're looking at around 150 to 200 megabits per second today, right? Then there was USB 1.0, 2.0, 3.0. Now you're also looking at solid state hard disk, which will offer much more storing, much more speed in terms of the storage. So in case of one computer, when you're trying to store and read data from the hard disk, the speed of this storage, the speed of at which you can read data depends much on the speed at which the hard disk operates. Right, hard disk, if it has mechanical components like magnetic readers, it is going to take time, and they cannot rotate faster than what what they could do. So obviously, in the sense, in that case, even if you have one computer and you must have seen, if you're trying to copy a DVD movie onto your hard disk, it might take sometimes half an hour. That is because the amount of data that you can save, the amount of data that you can save per second or per minute onto the hard disk is less compared to the volume of data. Now, if your volume of data becomes huge, right, then you might end up, for example, Netflix. They have lots of movies, right? They have to solve this problem where they have these movies have to be streamed online to people, right? How they're doing it? Can they do it with one computer? Obviously not, because if they do it with one computer, they are limited by the hard disk speed itself. Then the next limit comes is the CPU limit. The next limit comes is the bandwidth. The bandwidth is generally, these terms, it's very important for administrators to understand. So the bandwidth is generally the amount of data that you can transfer from one computer to the other computer. Today, sometimes you also say the bandwidth is the amount of data that the internet service provider provides you. So in India here, we have 2 megabits per second, 8 megabits per second, 15 megabits per second plans, right? That means that we're talking about 15 megabits per second. So if Netflix have to stream movies across US for multiple customers, thousands of customers, and this data has to be streamed faster and faster, obviously the one line of bandwidth is not sufficient. So they have to go to multiple lines of connections, so that they can transmit movies. So these kinds of problems, like just simple business problem what Netflix is facing, it cannot be solved with one computer. They have to go with multiple computers. In fact, you would be amazed, or you can also guess how many computers that they use today. They have a cluster of about 10,000 Amazon virtual machines in order to stream movies. Okay, that's the kind of scale that people are looking at with this kind of data. This is not necessarily mean that they are using Hadoop, but we will come to Hadoop and then explain Hadoop fits into this paradigm very well. Okay, so all of you following me? Hello?
Yes.
Yes. Any? If you have any questions, you should ask me. Okay. So this is again a big picture, so you will understand. Not many people can be able to understand, read, and understand all this. Just summary of why we are going into, why we need distributed computing like Hadoop. Okay. All right. So you might have seen Shrek movie, right? Or you might have seen the Lord of the Rings movie. So these movies were done with cluster of computers, and the quality of images that were being served were very high quality. And no one has done this before in terms of number of characters, the complexity, the number of effects that has to be integrated, and the kind of movements all these characters requires, right? So, and if you see, you, for example, this particular one, distributed computing, where you have a lot of the range, you would see each of these people that are standing there on the as the soldiers, right? They, all of them have to move at the same time, and all of them have to be rendered with a high quality, right? So obviously these guys have used about 3200 computers running 24 hours in order to render these images. Complicated scenes can take up to 48 hours per frame to render, even on the fastest computer. But they've used this 2200 computers to render almost instantly and then make a movie. So the amount of disk space that they've used is about 72 trillion bytes, equivalent to about 36,000 typical home computers. So the backup space was about 500 trillion bytes. So even though, I mean, we enjoy this movie, but the kind of technology that goes in the background is quite astonishing, quite amazing, right? So let's also see, every day what we do here today in terms of internet. When you do a search on Google gets you results instantly. How is it that Google can get these results instantly? Are they storing all that before you actually make a search? So how can they do, how can they how can they give such those results such an instantly, right? Any ideas? I mean, I think I wanted this class to be a little bit more interactive. Okay, so if you can answer some of the questions that I asked, that will be awesome. So how do you think Google is doing that? Anyone? So if you look at 400 million websites today, Google is able to search any of these websites and present the output of the search in front of your eyes instantly. How Google is doing that? What kind of machines they have? What kind of technology they have? Any idea?
But definitely
Can you hear me?
high end machines definitely, and
Yes. So yes, so they use a lot of high-end machines, no doubt, but then ability of these machines to be used so well and so accurately, mostly more than 20,000 machines they use it, and they index the web, and they store the content in their local machines. So what I mean is that if I have my company Kathy Technologies, that whole content is cached in their computers, indexed. So when you search for Hadoop training, you might hit Kathy Technologies. So they're not actually at that time searching. They have already searched for all possible keywords, index the web, and kept the whole content with them, right? Almost the index is all with them. So just imagine if they have to search 400 million computers and get all the documents, and for every document they open, they have to go through this document in terms of the words, and each word is indexed, and then each link is traversed until they find the last link, and then they do page rank algorithm, right? So all this is done and by Google at an alarming speed, and then they do it every night, and they do it almost day in and day out. So this is done with Hadoop-like infrastructure. In fact, Google is the one who popularized the concept called MapReduce. Right. So the MapReduce, when they published the paper on MapReduce, everybody said, "Oh, this is interesting," and then Yahoo took that paper and then implemented Hadoop. That's how Hadoop was born. Okay, so then simulating internet-sized network for networking experiments. Yeah, Planet Lab is a huge networking infrastructure for simulating almost as big as internet size network within a lab. So they do it using a cluster of computers. Then speeding the content delivery, Akamai. So how many of you know about content delivery network? Anyway, so basically, if you are trying to download Hadoop, right, and if you're trying to reach Apache Hadoop servers, and if across the world so many people are trying to download those software, then that machine is going to crash, because so many people accessing that machine, and then not only in terms of the bandwidth but in terms of the CPU also, the machine cannot take it. So Akamai came up with a concept called caching at the edge of the network. Caching at the edge of the network. Caching means not as in money cache. It's more like keeping the software available in memory at every junction. At every junction, it's almost like a traffic cop, right? At every junction. So they try to put this copy of this software at every edge of the network. So if I'm looking at India, right, there is probably there are multiple exit routes, and then I go and hit some DNS server. So wherever I'm going to hit there, wherever the traffic is going, I put a copy there. So when I hit the Apache servers, I don't necessarily have to go all the way to Apache server and then download it. In fact, I'll be downloading it from some other network, some other server being hosted by Akamai. Okay, it's very popular. Lots of people use it, especially if you want to download .NET software, Hadoop software, Java software. Right, all this is being done much faster using Akamai network. Otherwise, we would be struggling to download that software, because every day hundreds of people will be downloading that. Okay, so these are some of the distributed problems that we can see today. Actually, we are using it without knowing to you. All right. So, just a brief history of computers. I think we'll walk faster. So, I wanted to give this so that you understand the challenges here. So, people started with parallel computing, right? They started, okay, let me do multiple instructions in one shot rather than one instruction, so that you can get double the capacity. That's how they started, and then gradually we started looking at thread parallelism, right? Threads, multiple threads have been introduced. So what it means is that, let's say you have a box, a Unix box or a Mac OS box or a Windows box, and you're trying to read some data from the hard disk, right? When you're trying to read some data from the hard disk, your program will try to connect to the file, open the file, and then read the data, right? That's typically the process. Now, the speed at which the CPU operates is different from the speed at which the disk operates. So it makes a request and then it has to wait. So in terms of the CPU time, right, even 1 millisecond is quite expensive. So even if the hard disk is taking 1 millisecond, the CPU is actually sleeping for 1000 milliseconds, or basically 1 millisecond it is sleeping. During that time, the CPU can do some other job. right? During that time, so during that time, when the CPU is waiting for the data from the hard disk, the CPU can actually do some other task. So that is where threads have come in, or processors have come in, where the operating system will time share the CPU between multiple processors, because the devices that the CPU works with, the network device, the USB device, the keyboard device, the hard disk, the display device, they are not as fast as the CPU. So when the CPU makes a request, it has to wait. But instead of waiting, the CPU can do some other job and hence allocate that particular compute time to some other process. That's how parallelism has been introduced. That's how we will see multitasking happens in our computers. That's how we will see more than one program can run simultaneously. Okay. So again, brief is, I'll skip this because it's not much use. But just remember that multitasking happens in a computer. Okay. Okay, so I want to you folks to understand what is the difference between parallel versus distributed computing. Right? In parallel, you will see a single CPU or multiple CPUs. You will see that instructions are getting executed one by one. They can be either single instruction, multiple data, or multiple instruction, multiple data. So the thing about parallel computing is that all these CPUs are in one box. They are not distinct boxes. All these CPUs are inside one box, which means that they can go ahead and design a high-speed communication link between CPUs. So Cisco does that for their switches and routers. Most of the networking equipment uses more than one processor, and they use a high-speed backplane. It's almost like a highway where the CPUs can exchange data and instructions. So multiple CPUs can effectively communicate together. Right? That is parallel computing. Whereas in a distributed computing, you don't see this architecture. You will see that multiple CPUs connected using a network can communicate. They have their own CPU, their own devices, their own memory, their own network, their own USB device, their own CD device, hard disk, everything. Everything is separate, but they're all multiple computers, autonomous computers, independently manageable, connected together. Right? That is the difference between parallel and distributed computing. In case of parallel computing, if you see that something has gone wrong, it is likely that the whole machine can go bad. It's likely that the whole machine can go bad, or you will only see certain pieces of CPUs working. It's almost like our HP or Canon printer, which gives fax, printing, scanning, wireless, USB, and all that. That's almost like a parallel computing. It can do several things at the same time. But if it goes bad, then the whole device becomes useless. You can only use part functions, and it's very difficult to repair things like that. So that's why people prefer distributed computing, and it's also expensive to make and build parallel computers. It takes specialized technology, specialized people to program and things like that. Whereas distributed computing, just one computer, Dell could do that in every time you make an order, they're like manufacturing PCs like hell, right? Within 2 days you can get your laptop once you order from the net. And like that, millions of people are ordering from Dell or HP. They are able to fabricate machines. So it's easy to build autonomous computer with single CPU or dual core CPU with hard disk, CD, USB, display, and things like that. But how do you make this distributed computing work? How do you make all these computers work? So that's where we're going next. Okay. So this is some small introduction. If somebody asks you, you're using distributed computing, you're using Hadoop. Do you know how a vector-based computation happens? So if you see a scalar, I'm sure all of you can see the picture, right? Hello? Hello?
Yes.
Hello, can you guys hear me?
Yes.
Okay, so you have to respond. Otherwise, I'll not be able to do justice. Okay, you have to be active. So we have to still figure out how to make sure that you guys will be able to do hands-on and then ask questions. So through online, I will show you how to do, but you still have to do on your own machines and come back with questions. Okay, at some point when we do the tutorials. All right, so in case of a scalar vector based operation, if you want to add two numbers, R1 and R2, the result is R3. And this is one operation. Now just imagine that if you want to do this at the same time, right? So what they did is they invented this vector operations where you, instead of giving one input, you give vector of inputs and you get vector of outputs. This is how parallel computing works. Okay, this picture is very interesting. I thought you could remember this. By the way, this is not how our i7 works. Okay, i7 doesn't do vector based operation. They may do it nowadays, I'm not sure. This is more for parallel computing, supercomputers, things like that. Okay, so I'll pass these slides to you guys. You can read it. I think let me cover some more topics. Okay, so what is distributed computing? A collection of independent computers that appears to users as a single coherent system. Uh, okay, so ask me questions if you're not able to understand. A distributed system consists of autonomous computers, independent and autonomous computers that communicate to a computer network. Computers interact with each other in order to achieve a common goal. A computer program that runs in a distributed system is called a distributed program. Distributed computing is the process of building distributed systems and writing distributed programs. Okay, so there is this one thing that you have to remember. Suppose you have 40 GB of data and you want to transfer. It's going to take a lot of time, right? Maybe an hour or 2 hours. And let's say you want to run a program on that data. You want to just read the data and do some calculations or analysis and then print a report. That is your goal. So your program is about a few kilobytes. When you write a Java program or a shell script or a MapReduce program, the program is about few kilobytes or the max 1 MB. So what people thought, instead of moving 40 GB from X to Y, so instead of moving 40 GB of data from that place to my computer and then do the computation and throw away that 40 GB and show the results. Instead of doing that, people said, let's move this 1 MB to the place where data is. Right? It's easy to move 1 MB, which is the program that does the calculations. Move this program to the place where data is. Move the program to the computer where the data is. So that way, you can transfer this program, the executable program, onto the computer where data is, and you can run that program on that computer and then analyze that 40 GB of data and then throw the results out onto my computer again. So this way, instead of moving the data, you are moving the program. In distributed computing, it is very, very common that you don't move the data so much. You just copy the data once and it is there for you all the time, in terms of warehouses, in terms of hard disk and things like that. You only move your program to the place where data is, you do the calculations and then return back. That's how things work in distributed computing. Do all of you understand this concept? Hello? Okay, it's very important because in Hadoop we do the same thing. We don't move the data. We only move the program to the place where data is. Okay, so that is what Hadoop does it too. So we'll discuss that. It's a very important concept. Okay. All right. So these are the characteristics. I think the important thing to remember is distributed system can fail because there are a number of computers in this distributed system, and there are a number of components in this whole one monolithic distributed system. There are many parts that can fail. Network can fail, right? If you're using 20,000 computers, all this, each computer has one hard disk. Even if 1% of hard disk fail every year or every day, you will see that out of 20,000 you will see about 20 of them are failing every day, right? Now how do we go and make sure that if you're running something, if you're running something on this computer and a hard disk fails, how do we make sure the computing never stops? How do we make sure that there is no break in the ability for you to compute or for your program to run? So some of these challenges are there. So the network can fail. The network can fail, the motherboard can get heated, the power supply associated with the computer can fail, right? Because the life of a computer is about 3 years, 3 to 5 years, right? And especially the servers. So if once the life is over, any of these components can fail. So a distributed computing system where you have a big data center with lots of computers, the distributed computing framework, one instance of a framework is Hadoop. Hadoop is a distributed computing framework. This framework should help you to compute or to do computation even if there are failures, even if there are network failures, things like that. So we will see in the next few classes how Hadoop, in spite of several failures, in spite of machines being failed, in spite of network being broken, in spite of hard disk being crashed, in spite of 5% of the machines going down, still Hadoop will execute your program, analyze the data, and get back you the results without fail. So that is the kind of framework that Hadoop gives you. Okay, we will discuss that in the next few classes. So the what are the challenges in distributed computing? Right, overhead of network communication. You might have seen that if you're downloading a 2 GB file in your home, then the network becomes slow. So your wife or kids will complain saying that the network speed is low. What are you doing, right? So the challenge is that you have only limited network bandwidth. So there is also, right? So how do you effectively utilize it, right? So for example, it is almost like a truck, right? The sole purpose of a truck is to carry goods, correct? So the size of the engine, the driving space, everything has to be less so that you can optimize the number of goods that the truck can carry. Similarly, in a distributed computing framework, when you are communicating across two machines, you are having two types of data. One is the actual data that you are trying to transfer, and the second is the overhead in terms of what the data is, what is its size, what is its size, what format the data is, who is sending it, where is my source, where is my destination, is it zipped, does the data have boundaries, if so how many boundaries, is it sequenced, or is it binary, is it text? So this kind of overhead, right? The overhead is the data about the data that is there. Just like as you see in a truck, the engine has to be there and it occupies some space, right? If engine occupies much less space, the driver occupies much less space, the truck can be optimized to transfer more goods. Similarly, if the overhead in terms of the metadata is minimized, the distributed computing framework can transfer more data faster and then give you better results. So the challenge is the network in the overhead in network communication. So then the second challenge is the processing time must be magnitude higher than the network communication time to make it work. Sometimes, right, we do, when we assign a task to some of our colleagues, they take 2-3 days to do the job. But if I do it myself, I'll probably finish it in half an hour. So this is the same thing. It means that the amount of time that the machine takes to process the data should be higher than the amount of time it takes to transfer the data from one machine to the machine. Okay, so it's simple. So we have to have a faster CPU so that we kind of ignore the amount of time the machines take to transfer the data than to compute itself. Then put as much as possible locally to avoid network bottlenecks. So it's almost like a supermarket, right? When you go to shopping, you try to find everything you need in one shop. So earlier, if supermarket was not there, then you have to go to rice store to get rice. You have to go to fancy store to get some fancy items, and you have to go to different shops, right? Similarly, if you are working on some possible sets of data, if all that data is managed together and your program can use all that sets at the same time, then your computer will be able to perform better. So that just like you finish shopping in supermarket first much faster, because in this case all the goods are in one place. It's called data locality. Similarly, in a distributed computing framework, if my data is in one machine and program is another machine, there is an overhead of transfer. Instead, if data and program both are in the same machine, then the computation will be faster. So that is what it is called, data locality. So you must understand this concept very clearly, because in Hadoop, when you're writing an execute, when you're running a batch script, when you're running some batch scripts to do some reports as an administrator, you would be knowing that the script may be running in one machine and the data could be or may not be in the same machine, right? So you will see some things like that. So your job would be to make sure that there is a data locality so that the program and data would be in the same machine. Okay, so these are some of the problems the distributed computing framework faces. Are you guys following me, right? Hello?
Yes.
Yes.
A little bit louder. So is it clear?
Yes.
I hope
Yes.
I hope the analogies are making you understand a little bit better, right?
Yes.
Yes.
Okay. Okay. So because see, this is all common sense. Hadoop is all common sense. They have not done something rocket science. They have taken the use cases that are available today in the daily use and try to convert that into a computing framework. That's all they did. But they did it with a they did it so effectively that 5 years ago people were struggling to write distributed programs. Today, after 2 days of training, people can write distributed programs. That is the beauty of Hadoop. That is why Hadoop is so popular. Okay, you guys understand that? Okay. So there are also misconceptions, right? When you buy a computer, you think that it's going to be there throughout your lifetime, but it is not like that. Anything can fail, right? So the network is unreliable. These are the misconceptions, right? In the sense you think always that in a distributed framework, network is reliable, network is secure, network is homogeneous, topology does not change, latency is zero, bandwidth is infinite, transport cost is zero, there is one administrator, there is inherent shared knowledge, right? These are the misconceptions. All these are not true in distributed computing. Network is unreliable, network is not secure, network is not homogeneous. You buy 10 computers today of one brand with some capacity, then you buy other 10 computers with a different band, different capacity, different network card, different hard disk capacity, different memory, different CPUs, different brand. Instead of Intel, you'll buy AMD. So network and compute is not homogeneous. They're not made of similar machines. They're made of different machines with different brands, different specifications, and different parts. So the failure rate could be completely different. The topology does not change. Topology means the way you can interconnect these computers can change as well. Latency is zero. Latency is about, when I speak here today, when you, the amount of time you folks are in US, right? The moment I utter a word here, there is a small delay before you can actually listen, right? That is called latency. So if it is going through satellite network, it is about few milliseconds. Yeah. So things like that. So that is called latency. So latency is there in terms of when people talk, how fast they respond. Bandwidth is not infinite. Bandwidth, again, as I said, bandwidth is a term that is used in multiple places. Between two computers, the amount of data that can get transferred is a bandwidth. Sometimes internet connection is a bandwidth, right? That is the kind of the word that people use for bandwidth. Transport cost is zero. So people assume that you can transfer data for cheap, but it is not so. Today I'm paying internet service provider 1,000 rupees per month for a 8 megabits per second link, and he offers me 40 GB. So the transport of data is not free. It costs money, especially for companies. Okay, and there is no one single administrator. There can be multiple. You guys, once you get jobs on Hadoop, you will see that there will be more than one administrator working in shifts, and all of them have to understand this distributed computing. There is inherent shared knowledge, right? So again, we assume that all of the systems are working together with a shared understanding, but that is not so. Each computer can be independently working on different things. Okay, so let's finish this piece important, so that tomorrow what we will do, we will continue with a small piece of this and get into a little bit more detail. So if you have a big task, right? If you have a big task, so in terms of, let's say, the big task is in terms of, let's say, you might have seen this small game called Spy Game, right? You are given a picture, right? A big picture in a book, and you have to identify small objects throughout that picture, right? So what we do as humans, we try to do it one after the other, right? We try to divide this whole picture into sections, correct? These sections, and then we try to go every section and see, okay, is this picture that I'm looking for, is this small picture that I'm looking for, is in this section or not? So I keep moving my eyes across the whole picture and try to identify whether the object that I'm looking for is in that section or not. So that's how we do it. So it takes time, right? Now if you were to give it the same job to computer, right? If one computer is doing it, it has to do the same thing. It has to do the similar fashion what humans do. So it has to divide the big picture into small pieces, and then every section of the picture it has to look deeper and do some image processing to identify whether a particular object is there or not, right? You understand the problem, right? Any questions here? Hello? Any questions? You understand this task that I'm putting in front of you? So what I'm only trying to say is that, let's say the terrorist bombs have happened, right, in Dilshuk Nagar in Hyderabad. So if somebody has to watch the video, they might have to watch the video for the past 1 month. Then maybe every day they're recorded for 6 hours, and 6 hours into 1 month is about 180 hours of video they have to watch, and they have to identify any uh, you know suspicious activity in that video. So if humans have to do it, they will take 180 hours, and they cannot do it continuously. They have to break it into pieces. Now if multiple people, so what they do is they employ multiple people to watch those 180 hours of data. That's all distributed computing is. So what we're trying to do is we're dividing the problem into small tasks, and then each task is assigned to one person or one computer, and let the computer does the task. And then once all these people completes their task, they come back and then do some aggregation. They come back and then decide, okay, I watched this 2 hours video, there's this suspicious activity, I can probably do this one more time. So the other person says that is there is not much of suspicious activity there, So there's useless video that will. So things like that. So out of this 180 hours, you might see there will be 2-3 hours of video that may be very interesting, right? You have reduced the size of the video from 180 hours to 2-3 hours of important data. So similarly, in a distributed program, you may have so much of data, and once you assign this data to multiple computers, they do number crunching, they do analyze the data and reduce the amount of valuable data in terms of either reports or in terms of insights or in terms of business knowledge into a much smaller size. So that is called joining the data from multiple data sources into one. So again, so in order to write a distributed program, first you have to identify the problem. The problem here is image recognition or object recognition inside a picture. You are dividing this picture into pieces. Each task is one section, right? And each section is assigned to one computer, and one computer can do image processing. Okay, so all these tasks, once they are complete, right, and then after they complete, they have to intimate the master that we have done the job, and then the results would be correlated. So this is how it works. So you have a piece of work, and then you divide it into multiple pieces, right? You partition the tasks. Okay, so this is one idea. The second idea is, again, each work is given to a thread, right? If it has if you have a 4 processor system, you can give 4 tasks to that to that machine at the same time, right? So that's how it works. So each thread will take one work and then complete the work, and then once the work is done, the results are assembled, right? Results are assembled. So now this model seems to be very simple, right? The model that we just discussed, you understand, right? This slide is very important. Okay, so you've got some work, you divide it into pieces, you assign it to multiple computers, and all them did a job, and then you assemble the results together. So all of you can see this picture, right? Okay, so there are some problems with this idea of parallelization. First problem is, how do I assign work units to worker threads, right? So how do I assign, meaning that I should not assign the same work to multiple people. And if I assign a work to someone, that work should not be assigned to a different worker. So I had to balance between the number of work units to work threads, right? That is one thing that I need to understand. What if we have more work units than the number of threads, right? So then what we do is you have to somehow manage these work units among these threads. So you have to distribute the work among threads so that each thread will get enough work so that they are not idle. Once the work is done by these threads, you have to aggregate the results. Aggregate means you have to keep all these results together. The fourth one, how do you know that all the workers have finished? So one worker may be sick and then he will not respond. How do you know that all workers have finished, right? So what if one of the worker does not respond at all, right? Then there is another fundamental problem. What if this work cannot be divided at all? So this is a work that one person have to do it, and you cannot divide the work at all. So you have to find answers to this in order to do effective distributed programming. And Hadoop does that very effectively, right? Hadoop does it very effectively. We'll see in next few classes how Hadoop does it. You understand this problem, right? This is very important. Okay, all of you, can you hear me? Okay, so you have to understand this is not an easy job. Of parallelizing a task is not an easy job because of these challenges, because the number of work units could be more or less. Each of these thread could be different capacity also. There may be some computers which are powerful in the system. There are some computers which have more memory, right? In that case, how do you assign more work to them? If you don't assign more work to them, then the system becomes idle. The system becomes idle, then your CIO says that why are you keeping this system idle? There is a compute power being wasted. You have to utilize the system to the maximum. How do you make sure all this happens in a distributed computing framework? So a framework that can solve some of these problems effectively is called distributed computing framework, and Hadoop is one such framework. Okay. All right. So some more. So there is one more important concept I want you to understand. Okay. Each of these problems represent a point at which multiple threads must communicate with one another. So again, once all these results are available, they have to be assembled at one point. That means these computers have to communicate with each other, right? They have to synchronize. They have to talk to each other and then aggregate the results. And there is a problem there. There is a problem there. The problem is here like this. For example, this is a small program, and there are two variables y and x, right? And these two threads are working on the same data set y and x. So if thread 1 is running and thread 2 is running, so what we are doing in this thread 1, we have a small operation here. We are incrementing x by 1 and we are assigning x to y. Whereas in thread 2, we are incrementing y and we are assigning x to 3, right? Now, if y is equal to 0 and x is equal to 6, what are the final values of y and x after these two threads finishes? Can you guys predict? Can you guys tell me the answer? If a equal to 0 and x is equal to 6 at the start of a program,
So it depends. It depends on which thread is running first.
it depends on the thread is running first. That is correct, because it's unpredictable. Because which thread runs at what time, we don't know. Okay. So this problem is prevalent in distributed computing, right? When you are assigning a work to worker unit, you have to first lock the queue. You have to make sure that it's assigned to only one person, right? What if two persons take it from the queue? It will be a problem, correct? Things like that. So to explain it further, each of those instructions actually are not just one. There are multiple instructions. So when you run a multi-threaded program like this, we don't know what order these threads run, nor do we know when they get interrupted. So thread 1 may interrupt thread 2, or thread 2 may interrupt thread 1. So it's very, even though it looks like a very simple one-step operation, in a distributed framework, in a multi-threaded environment, things could get very complex. Okay. So end of the day, multi-threaded programs means unpredictability. So this applied to, not only this does not apply just to simple thread that we saw, it applies to multiple problems, right? For example, pulling work units from a queue, reporting the work back to the master unit, telling another thread that it can begin the next phase of processing. All these things require some kind of synchronization, right? Then you have synchronization primitives, right? So just like traffic cop in the junction, you have synchronization primitives in the operating system that a process can say, okay, instead of rushing together on a traffic junction and then having a deadlock, the traffic police can divert the traffic in a more synchronized fashion. Similarly, if the road is same and multiple people are using the road, similarly, if in a process, if there is one object or data and everybody is trying to access the data, you need a traffic cop, right? That is called synchronization. So those traffic cops are nothing but, in Unix we call it as semaphores. Okay, in Unix we call it as semaphores. It is almost like a traffic cop in the junction. So it helps you to say, wait, the other guy is using this junction. So once that guy is completed using it, then the other people can use it, right? Things like that. So you have all this. I just this particular same material is being taught to Triple IT Hyderabad students in Hyderabad. So they're more since it is a course that spans for about 3 months, I go a little bit in depth. So I think for you folks, it is not that important to get in depth, but you must understand that this traffic cop is required, especially when you have a shared resource in a distributed computing framework. And in a distributed computing framework, everything is shared, hence you need a lot of traffic cops. Okay, that is the message that you should take. Okay, so again, so the locking happens. The traffic cop is basically asking people to stop. Here in the operating system, the semaphores are being used like a traffic cop, and they're locking a particular section of the code and then unlocking the section of the code so that each of these threads can run predictably. There are also condition variables. This is again a programming concept being used as traffic cops, and this is the final example using conditional variables. Some people, you also put barriers. So barrier knows in advance how many threads it should wait for. So so in a complicated system, when a lot of things are happening parallelly, there could be multiple joins, multiple people waiting for multiple things to happen. Similarly, multiple computers waiting for different sets of tasks to complete and wait. And there can be so many such things happening. So you need programming concepts where each of these threads can wait for other threads to finish the task so that all of them can be aggregated. So the concept called barriers is there. Okay, so again this slide I can skip. Barriers I can skip again. So there are multiple barriers. You can put a barrier and then the barriers can repeat themselves. It can become a butterfly barrier. Right? Too much synchronization, sometimes too much synchronization also gives a deadlock, right? So we have to be very careful. And so traffic cop has to do his job properly. If he forgets to do it, there could be a deadlock. So end of the day, what we are saying, distributed computing is not an easy thing. It is very hard. And that is why people have not done it for so many years. But over the years, people have mastered the art of distributed computing, and frameworks like Hadoop have made the distributed computing much easier to do. Hence, people can do distributed computing today with just few computers together and then process large amount of data. There's another problem. If there are any bugs in the system, in a distributed computing system, it's very difficult to fix. It's not easy to fix a bug in distributed computing system. So the monitoring, the debugging capabilities have to be very good in order to understand the problem and see what is happening. So especially as Hadoop administrators, if you think some developer will say, I don't know, the job was working yesterday, but it is failing today. So we administrators will become clueless. What is happening? Yesterday, if it is working, it should work today. Right? But between yesterday and today, there could be things that have changed in your database, in your system, in your cluster, in your data center, right? So there may be a hard disk has been removed and his data is not available. Maybe permissions for the data or hard disk that he has got is not there, right? Things like that. So there may be several things that are possible in system where the administrators have to be responsible. So you will have tools to see what is happening within the system. Okay, so we'll also see some tools moving forward. Okay, so as we said, distributed computing is hard, but Hadoop is going to make it easy for you. And this Hadoop is built on the concept called a MapReduce. So the MapReduce we'll discuss tomorrow. The MapReduce concepts we'll discuss tomorrow. And so the Google has built their entire search empire using this concept called MapReduce. Their whole business runs on this concept called MapReduce even today. And then sometime 5 or 7 years ago, they wrote this paper on Hadoop and published to IEEE. And that is where people started using the power of MapReduce. That's where Yahoo started building their own framework. They built it for several years. And Dow Cutting, one of the main designer developer for Hadoop, actually implemented MapReduce algorithm at Yahoo. And at some point, Yahoo said that, okay, let's not keep the source with us, let's open source it. they open sourced it, and then that's how people started using Hadoop, and that's how we are here trying to learn Hadoop so that we can understand and do a lot of distributed computing. All right, so that's the end of the class today. Is it clear? Any questions? Hello? Hello? Hello?
Hello. No questions ready.
Okay, so I hope you guys are comfortable so far. If you have any issues, I want you to explicitly say it aloud so that we can address it. Because this is the first time I'm doing an online course. I've done several physical courses, but not online course. So I don't know the dynamics completely in terms of online course. I'll try to be as effective as in terms of pictures and as vocal as possible so that you guys can understand. But if you don't understand anything, you should explicitly flag immediately.
Sure. Thank you.
Okay, guys, that's all for today. I think if you have any questions, you can send me an email. I will address those questions in the next class. Okay, so I will do a recap next time when we come, and then we'll start with MapReduce and Hadoop. Okay, so I hope you guys understood the concepts of distributed computing. Okay, the challenges. You don't have to know detail. You have to know some of the challenges and why it is important to understand the background behind it. Okay.
Thank you.
Okay.
All right. So I'm exiting now. Thanks, guys.
Well, thank you. Appreciate it.
Thank you. Appreciate it. Yep.